All right, okay, now this is where we left. We were supposed to do question number 10.2 from part number 2, right? So now let us start with by reading the question first for 5 marks. Now 10.2 is as follows. They say to us, a magnetite consists of 72.41% iron and 27.59% oxygen. Determine the empirical formula of magnetite, right? So we expect to have something that looks like this, Fe, Fe, O. So we don't know what is the number here. We also do not know what is the number over here because they say magnetite, which is a product when iron reacts with water, it forms a magnetite. So apparently magnetite is a composition of two elements, which is iron and oxygen, because you can see that the hydrogen will be released in a form of gas, okay? So we don't know the numerical value, the subscripts, we don't know the subscripts of Fe and O2. That's what we are looking for to determine the empirical formula. So now, how do we determine the empirical formula? We are given the percentage of each ion. So we're going to assume that all of these, because when you add them, it's 100%. We're going to assume that the mass of the compound, which is FeO, it is 100 grams. So if we assume that, so that means these percentages will be given in a form, will be converted in a form of mass. Okay, so that means if that's what we assume, that means we're gonna have a mass of the percentage. We have Fe, which is our ion. Remember, we are answering 10.2. Fe, which is our ion, they said we have how much percentage? 72.41%. So this will correspond to mass. That means will be 72.41 grams. Now, the oxygen, it is given to be which percentage? 20, magnetite has 27.59% of oxygen in it, will also be considered as mass. So that means will be 27.59 grams. That means the whole compound, its mass is 100 grams, because when you add this, they will most definitely give you 100 grams. Okay. All right. So now this is what we are going to do. We are going to determine the number of moles, which is the subscripts over here for Fe and O2. But how are we going to do that? Now, let us start with Fe. How do we determine number of moles of Fe? Number of moles of Fe, we're going to say, because we have mass, right? We're going to say mass over molar mass, right? So now mass of Fe in terms of percentage, but now it's converted into grams. It's going to be 72.41 grams divided by molar mass of Fe from the periodic table. Let me check my periodic table here. It's 50 Fe 56. So here we're gonna write 56, and therefore what is 72? 72.41 divided by 56, I get to 2 decimal places, I get 1.29. And therefore, what will be the number of moles of oxygen? Now we're talking about oxygen. We're gonna use mass over molar mass, and mass for oxygen will be 27.59 grams divided by molar mass of oxygen. We know that it's 16, right? So that means we're gonna say 29.59 divided by 16, and therefore to 2 decimal places we get 1.72. Now we're going to compare the number of moles, okay? So remember, we are looking for Fe is to oxygen, right? So now we need the subscripts over there. So for Fe, we have 1.29 is to, for oxygen, we have 1.72. Now we know that when we're looking for a ratio, we divide by the smallest number amongst the two numbers. So the smallest number between this is 1,29. So that means on this side of ratio, I'm going to divide by 1,29. Same applies to there. I'm going to divide by 1,29. 1,29, 1,29, I get 1:2. So now on my calculator, 1,72 divide by 1,29. I get 4/3. I get 4/3. I love expressing them in fractions, which is 1,33333. So now we can see that in order for us to eliminate this fraction over here, we're going to have to multiply by 3 so that 4 falls down, okay? Because we can have something like this. So on both sides, I'm going to multiply by 3. On both sides, I'm going to multiply by 3. 3 multiplied by 1 is going to be 3:2. 3 will cancel 3, and then I'm going to left with 4. So that means my ratio will be 3:4. Therefore, my final answer, the empirical formula for magnetite, it will be Fe. Fe is 3, and oxygen will be 4. And therefore, we are done for 5 marks. That's how we solve this question. Now we move to question number 11. Okay. Now, question number 11, it reads as follows: acids and bases. So it says, define an acid in terms of Laurie-Bousted theory. These guys, they are 100% correct. How does acid and base actually behaves? We know we have acid and bases in terms of Arrhenius theory. So Arrhenius theory, it is not 100% correct because Arrhenius theory says bases form OH minus ions in a solution, but not all bases that form that, like ammonia. Ammonia in water, it doesn't form, not ammonia, what is this thing? The other bases, when they dissociate, they do not form OH minus ions. So Arrhenius is not 100% because it doesn't encompasses all of the behavior of the bases. So these two guys over here, they're 100% correct. When they say acid, it's a proton donor, base is a proton acceptor. This is how I used to remember them, like how I would make sense. Hannah, how do you define? Because you can confuse these guys, you see. So what I do is, oh, Laurie-Bousted, when I see two names, I know they are correct. And the correct way to define an acid is to say acid is a proton donor, base is a proton acceptor. Simple as that. When I see these two guys, I know acid is a proton donor, base is a proton acceptor. But if I know it's one guy, which is Arrhenius theory, I know base forms hydroxide ions in water, acid forms H plus ions in water. So that's how I am able to distinguish all of these theories so that I do not get confused. So now 11.1, it says to us, define an acid in terms of Laurie-Bousted theory. You're going to say acid is a proton donor. That's it. That's how we define acid, okay? And then 11.2, they say to us, consider the following acid-base reactions. Okay, there are many different types of reactions, but here we are talking about acids and bases. So now we can see that sulfuric acid will react with water to form HSO4 minus ions plus H3O plus ions. Now the second equation, the H2SO4, actually it's supposed to be this. Here it's supposed to be minus. They forgot to minus over there. Here it's supposed to be minus. It's a dibotic acid. It reacts 2 times to form this, okay? So that means here's supposed to be minus to show that one acid has been donated to water. So H2SO4 minus again will undergo another cycle by reacting with water to form SO4 2 minus plus H3O plus ion. So it's a dibotic acid. That's why it has to donate 2 times, okay? All right. So now 11.2.1, here we have 11.2.1. Identify one conjugate acid-base pair in reaction number 2 above. So we go to reaction number 2. The only thing that we want is acid-base pair conjugate. Right? So now, you can choose this and that. You can choose this and that. Really, it's up to you, Shane. However you want to choose it. Okay, so that means if I choose this and that, identify one, they just only want one from reaction number 2. So I'm choosing this to that, because this it's an acid, right? Because it's gonna have to donate its proton there to form that. So this, when donates proton, it turns into that. So these are the partners, right? It's one thing, just that here it donated, and then so this will be acid, and then here will be conjugate base, because when this reaction it takes a reverse, that means this will have to act as a base by accepting a proton to form this, according to this theory. So we can just say it's HSO4 minus and SO4 2 minus, or you can take H2O and H3O plus ions. Okay, can take them if you want to. They just said 1. Now 11.2.2, they say to us, identify one, again, substance in the above reaction that is an ampholyte. An ampholyte is a substance that can act as either acid or base. So to make things easier, just take your water to make life much more easier. So above them, you can take even this, it's an ampholyte. It can act as a base. You see, it can act as a base for this reverse reaction. It can act as an acid for this forward reaction. You see that? So you can take H2, you can take HSO4 minus, or you can take water. It's up to you. Life to be easy, take water. 11.3. Now, the same magnesium carbonate, MgCO3, is one of the active ingredients found in antacid medication used to treat ingestion and acid reflexes. We are doctors now. You see, chemists can work with doctors. MgCO3 reacts with HCl according to the following balanced equation. Oh my God, chemistry is so nice. So MgCO3 react with HCl to form MgCl and H2O plus carbon dioxide. The mass of the magnesium carbonate found in each antacid tablet is 0.15 grams, right? Now, calculate the volume of carbon dioxide gas formed when one such an acid tablet reacts with excess HCl at STP. Guys, you'll be forming tablets anytime soon. So you really need to love these things. They're nice. At STP, that's very important. So now we have chemical reaction, right? And now in this chemical reaction, we are not into the biology stuff and so forth. We're just doing calculations. So for 5 marks, we need to calculate the volume of carbon dioxide at STP if we have excess. So that means this will be limiting reagent. MgCO3, chemists, they know this will be a limiting reagent, and therefore this will be an excess one. So that means we use limiting reagent to determine everything on this chemical reaction. So, but because we're focusing on carbon dioxide, we want to determine the volume of carbon dioxide at standard temperature and the pressure. We're going to use a molar volume, which is denoted by 4 cubic decimeters. Okay, so now this is what is happening. Before we can calculate the volume of carbon dioxide, we need number of moles of carbon dioxide. You know why? Because the formula that we're gonna use at STP, it is this formula. Number of moles is equals to volume divided by molar volume. So the units for molar volume actually, it is cubic decimeter per mole. This is the units for molar volume, hence why molar volume. Okay, so this is the formula that we're going to use to determine the volume of carbon dioxide at STP, standard temperature and pressure. We use this. You know, when they say at STP, the temperature, it is 273.15 Kelvin, and the pressure, it is 180 M. Okay, so when you use that formula, your PV is equals to nRT, and you determine volume, you're gonna get this number, 22.43. And so I standard pressure, standard temperature, and then R will be constant most definitely, and therefore V over N, this will be a molar volume, and this side you're gonna have RT over P. I'm just showing you where does this value actually comes from. That's how we determine the molar volume. Okay, oh my God, the chemistry is so nice. So now In order for us to use this formula, like I said, you're gonna need number of moles of carbon dioxide. So how are you going to do that? We're gonna use limiting reagent. Oh my God, we're gonna use the limiting reagent. With our limiting reagent, what is actually provided? Let us read 11.4. They say 11.4, a solution of magnesium hydroxide. Ah, what am I doing? I'm lying. We are given the mass. So the mass of magnesium carbonate, it is given to be 1,5. The mass of magnesium carbonate, it's given to be 0,15 grams. So we're going to convert this mass into number of moles. This is our limiting reagent, right? So to determine the number of moles, we need the molar mass. Okay, we can just use the formula. Number of moles is number of moles of magnesium. Let me write it. Number of moles of magnesium carbonate is equals to mass of magnesium carbonate divided by the molar mass of magnesium carbonate. What is the mass of magnesium carbonate? It's 0,15 grams. Remember, in chemistry, we use grams, but in physics, we use kilograms. Now, what is the molar mass of magnesium carbonate? You go to your periodic table, the atomic mass of magnesium, let me see here, it's 24. We have 24, and then carbon, we know it's going to be 12, and then oxygen, it's 16, but we have 3 oxygens. We're going to say 3 multiplied by 16. Oh, 16. And therefore, what will be the number of moles of magnesium carbonate? Do not forget, magnesium carbonate is the limiting reagent because they said HCl is in excess. So we're going to say 0,15 divide by 24 plus 12 plus 3 multiplied by 16. And how much do we get? We get to 2 decimal places, 1,79 times 10 to the power of -3 moles. This is the number of moles of magnesium carbonate. So now we know the number of moles of our limiting reagent. We can determine the number of moles of anything now. Like you can determine number of moles of HCl, MgL. Oh, shame. Now we want to talk about carbon dioxide. Let's determine number of moles of carbon dioxide. This chemical equation is balanced, and we are told. So, but I was told that even though the chemical equation is balanced, check it very already. It is balanced. Apparently, this balanced. Shame, we don't have that time. But we are told. So number of moles of carbon dioxide will be the same as number of moles of magnesium carbonate. Why am I saying that? Because the stoichiometric coefficient for magnesium carbonate is 1. The stoichiometric coefficient for carbon dioxide, it is also 1. So that means they have the same number of moles. So in this case, what will be the number of moles of carbon dioxide will be the same as 1,79 times 10 to the power of -3 moles. Now I know number of moles of carbon dioxide. How good is this? Now we can determine the volume of carbon dioxide at STP because we know the molar volume at STP is 22,43 cubic decimeters. So now let us determine that. I'm going to make V subject of the formula. I'm going to cross multiply. So that means volume of carbon dioxide will be the same as number of moles of carbon dioxide multiplied by molar volume. So now what will be the number of moles of carbon dioxide? It's 1,79 times 10 to the power of -3 moles. I want to show you something. And therefore the molar volume, it's 22,4 cubic decimeters per mole. And then I divide. So mole cancel mole, and therefore that's what I wanted to show you. We're gonna left with cubic decimeters, which is the units for volume. So that means we're gonna say our final answer. I can just say my answer because I remember my answer was, because this is not even final answer, even though we rounded it to be. So you can just say your answer multiplied by 22,4. And then we get 0,04 cubic decimeters. This will be the final answer. How beautiful is this? Super beautiful. I hope you, my learners, are enjoying this as well. Maybe hopefully one day you'll be chemical engineers. Now, 11.4. 11.4, it says to us, a solution of magnesium hydroxide is prepared by dissolving 8 grams solid of magnesium hydroxide in water to make 250 cubic centimeters of the solution. Before I can even, you know what I hate? I hate making mistakes. So this is what I always do. Before I start by converting this, let me say my volume is no longer this. I'm going to divide this by 1,000. It's going to be 0.25 cubic decimeters. That's the first thing, because I start by eliminating things that I know they will make me do mistakes. I start by eliminating them. I don't like this. So grams, I'm happy. Okay, let's start. A solution of magnesium hydroxide is prepared. So a solution is combination of something in solid and water, and then like water and salt, or water and sugar, and it dissolves. That's a solution, right? Solvent is water, solute it's sugar, and therefore solute plus solvent, they form solution. Ne? Right. So they're gonna take 8 grams of this thing in water, right? And this thing will dissolve in water, and then the volume of everything, it will be 0.25 cubic decimeters. Now we can calculate the concentration, because you know the concentration is number of moles divided by volume. But number of moles, we are given mass. We know if mass given, number of moles given is the same thing. We can interchange from mass to moles, from moles to mass. We can just play shame. So assume that magnesium hydroxide dissolves completely. Okay, thank you. This solution reacts completely with a sample of impure ammonium chloride according to the following balanced chemical equation. So apparently the solution that we prepared here, it will react with impure ammonium chloride. When they say impure, that means it is not purely ammonium chloride. It has other substances attached to it. You will see when you work at the mines as chemical engineers, you're gonna work with impurities where you're gonna have to extract. Oh my God. So when this reacts with this will be products that will be formed. The percentage purity of ammonium chloride sample is 99.95%. This is a very high percentage. So that means we didn't lose much as chemical engineers. So now calculate the concentration of magnesium hydroxide solution for 3 marks. Okay. That was a long story. I hope you didn't lose me along the way. So 11.4.1. I can't be enjoying myself and you are not enjoying there. Calculate the concentration of magnesium hydroxide solution. I said to you, this is magnesium hydroxide solution, and in here we were preparing the solution, right? So we are preparing it for this volume and this mass. So to calculate the concentration, we know that we use the formula that says C is equals to N over V. But the problem is for our magnesium hydroxide, we have the mass, not the moles. But stoichiometrically, we know how to calculate number of moles. We say it is mass over molar mass multiplied by volume. Okay, this is the same as the formula that we can use to calculate the concentration. Now, what is the mass of magnesium hydroxide? It is 8 grams. And then what is the molar mass of magnesium hydroxide? MgOH2. So you go to your periodic table, we said magnesium, let me confirm again, we said magnesium is 24. We said it's 24, so we're gonna say 24 plus, you can just write 2 here and open bracket because of these 2. Okay, oxygen is 16 and hydrogen it is 1. Close your bracket. Let me extend my fraction, and then the volume in cubic decimeter, it's 0.25 cubic decimeters, and therefore we just punch everything on our calculator. We say 8 divided by what? Let me see. 24 plus 2 open brackets, 17. I'm not going to say 16. I can say 17 because 16 plus 1 is 17. Multiply by 0.25. Now, what will be the final answer here? To 2 decimal places, we get 0.55 mole per cubic decimeters. Do not forget your units. That's very important. So this will be concentration for magnesium hydroxide solution. 3 marks. And then 11.4.2, it says to us, For 6 marks, calculate the mass of impure ammonium chloride in the sample. I love this. Now we know what's happening here, right? So we are given the percentage purity. The percentage purity, let me write it where? Here. The formula that we use to calculate the percentage purity, not the purity for kids, man, that thing, no, not that thing. Percentage purity is equals to pure over impure. I'm just writing it like this so that you do not forget. Multiply by 100%. Guys, I hope you're gonna do chemistry. So percentage purity is the same as pure sample over impure sample. Okay. So that means because here we have impure sodium chloride. So that means here we are talking about percentage purity of pure sodium chloride. That means we need pure mass of sodium chloride or pure number of moles. Does not matter whether you use number of moles or mass, it is still fine. So we need pure mass of sodium chloride, ammonium chloride, and then here it's impure mass of ammonium chloride. So they want us to calculate the impure mass. So that means this is what we are looking for, impure mass. So that means in order for us, we are given percentage purity that it's 90.95%. So we need pure mass. How are you going to get pure mass of this thing, of ammonium chloride? So in this chemical reaction, the only thing that can react with magnesium hydroxide from the reactant side, it's a pure mass. Okay, that means the other things that are with sodium chloride, they are not going to react with magnesium hydroxide. The only thing that's going to react with magnesium hydroxide from here, it's a pure sodium chloride. So that means the mass that we're going to get here is a pure mass. So how are you going to calculate that pure mass? We're going to use magnesium hydroxide. So from this concentration, or from however, we're going to need number of moles of magnesium hydroxide, and these number of moles, they're going to help us. However you want to calculate your number of moles, you can use the very same formula because, or we can use that one, molar mass, blah, 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 it is still fine. So to calculate the number of moles of magnesium hydroxide, I'm going to use this formula, which is N of magnesium hydroxide is equals to C multiplied by V. So I said my C is 0.55 multiplied by V. We said it's 0.25. It's fine. You can use this formula. N is equals to mass over molar mass. It is still fine. So now I'm going to say my answer multiplied by 0.25. Apparently, I get to 2 decimal places, I get 0.14 moles to 2 decimal places. This is what I get. Fine, this is the number of moles of magnesium hydroxide. But I do not need number of moles. For now, I need number of moles of this so that I can determine mass. You see, which is the pure mass. So what is the number of moles of this thing? According to a balanced chemical reaction, I want to determine the number of moles of NH4Cl. So how many moles do I have there? It's 2. So I need 2. How many moles? So which number of moles am I going to use? I'm going to use number of moles of magnesium hydroxide, which is only 1. You can start here. It's fine. If you don't understand this, you can do that thing, a ratio. You can say NH4Cl is 2 number of moles, right? MgOH, and then you say 1, you say this one is 2, right? What's it with my laptop? This one is 2, right? You can write 2 over here is 2, that one is 1, you can write 1 over there, and therefore the calculated number of moles of this is 0.15, and you cross multiply. It is still the same thing. You can do it in that way. So number of moles of N what? NH4Cl will be equals to 2 multiplied by what? What is the number of moles of MgOH? We said it's 0.14. 0.14. And therefore, we're going to have 0.28, right? Yes. Let me do with my calculator. 0.4 multiplied by 0, multiplied by 2. Yes, it's 0.28 moles. Now let's determine mass of this thing. Okay, so to determine mass, we're gonna say number of moles is equals to mass over molar mass, and therefore mass will be equals to number of moles multiplied by molar mass, and then the number of moles of sodium chloride is 0.28, and then the molar mass for that thing is gonna be how much? We're gonna say nitrogen it's 14, I know, multiply by 4 for hydrogen, which is 1, plus Cl, which is 35.5, right? Yeah, 35.5. And therefore, what will be the mass? We're going to say 0.288 multiplied by 14 plus 4 plus 35.5. And then we get 14.42. This is the mass, actually. This is the mass of ammonium chloride. And this is the pure mass of ammonium chloride that has reacted. Now, the percentage purity is equals to pure mass of NH4Cl divided by impure mass of the very same NH4Cl. Sorry, I don't have space, and you write multiply by 100. I showed you the formula. This is the formula, multiply by 100, okay? Multiply by 100. Now, what is the percentage purity? They said it's 90.95. So you're gonna say it's 90.95. For a fact that you write percent here, you can also write it's fine. So what is the pure mass of this thing? We said it's 14.42 divided by the impure mass of NH4Cl multiplied by 100%. We divide both sides by 100%, and then here we're going to get 0.9095, and then here we're going to get 14.42 divided by impure, I'm just saying MP, mass of NH4Cl. And therefore, we cross multiply. Let me write, yeah, record, I don't have space. Let me write here. So now I'm gonna say, this is the same over 1. This multiplied by that is gonna be 14.42, right? That's what we got. And then here we're gonna have 0.9059 impure mass of NH4Cl. You see, now I don't have space, you write the correct thing. So I'm going to say 14.42 divided by 0.0905. Here it's 95. And then I get that impure mass of NH4Cl will be 15.85 grams. That will be 11.4.2.